So now that we've talked about the Helmholtz energy, we're going to move on to the thermodynamic function, state function defined by Josiah Willard Gibbs, that's named after him, the Gibbs energy, which is often the one that's much more useful in terms of chemistry when we're thinking about chemical reactions, because this one is intended to be used for processes that occur at constant temperature and pressure, which is usually what we're dealing with as chemists. We're running our reactions at a constant temperature, usually having some sort of heat bath, or just running it in the room temperature, and the pressure is usually just atmospheric pressure. One just fun thing to note about Gibbs is that he is from Connecticut, so just down the road from us in New Haven, and spent most of his, or I think all of his scientific career at Yale. So he did a lot of work with regards to chemical thermodynamics. This is not the only place his name shows up in this class. So he did a lot of the work on the underpinnings of the things that we're talking about in this class. So this is a Connecticut homegrown science that we're looking at here. Okay, so again, we're going to start with the first law, du equals dq plus dw, right? We know that's true. And we're going to, again, implement the second law, right? So ds is greater than or equal to dq over t, right? Where if it's equal if we have a reversible process, but it's greater than q for an irreversible process, q over t. And then we need to also now, work can happen because volume can change, right? This is not now a constant volume process, this is constant pressure. And so we need to define the work. And that for a reversible process is equal to minus p dv. So we can go ahead and substitute these in. We can say du has to be less than or equal to, and we're again going to do the same thing we did before, bring the temperature over, TdS has to be greater than or equal to dq, so we can flip the sign around if we, right. So du has to be less than or equal to TdS minus p dv, and then we can rearrange this to have everything in terms of 0. Right, so we can say du minus TdS plus pdv has to be less than or equal to 0. Right, and I will again emphasize this is at constant temperature and pressure. Okay, so that now gets a lot, we have now 3 terms here. We'd like to simplify this into another state function, just like we did with the Helmholtz energy. And so we can think about taking the derivative of all this, right? D of u minus ts plus pv, right? We add all these together. And let's think about this derivative. All right, so the first term in it is du, and then we'll have 2 cross terms for each of these products, right? Ts and pv. So we get minus tds minus sdt. So this is, like the product rule that you learned for derivatives. Then we'll also have plus pdv plus vdp. Okay, but we have a couple of these terms. We're considering a process that is at constant temperature and pressure, so anything that has a change in temperature and pressure goes to 0. This term goes to 0, this term goes to 0, and we can see that the derivative of this whole thing at constant temperature and pressure is this right here. So we're going to take this part in here, and this is going to be our new state function, right? So this is another case where we have something composed entirely of state functions, so the result is also a state function. And this is what we're going to define as the Gibbs energy, G. All right, and so the Gibbs energy is equal to U minus Ts plus PV. So that's one way of defining the Gibbs energy. One other thing you may recognize is that we can take the U plus PV part of it. That's another thermodynamic function that we have defined. All right, so we can remind ourselves that enthalpy is equal to U plus PV. And so we can also write that G is equal to H minus Ts. The other thing we can do is we can use the definition of the Helmholtz energy that we just looked at and say, oh, well, U minus Ts, that's equal to A. So we can also write this as A plus PV. So multiple ways of writing out the Gibbs energy, but ultimately it's this combination of state functions. So again, we have a state function, and the ultimate result is that we've included the second law here, and we can say that the change in G has to be less than or equal to 0. And that tells us again, for a constant temperature and pressure process, that it'll be, again, the less than applies to a spontaneous process. So a process can only be spontaneous if its change in Gibbs energy is less than 0 for a constant temperature and pressure process. And it will be equal for a reversible or for equilibrium. Again, those are sort of interchangeable process. And this idea of the change in Gibbs energy being equal to 0 for equilibrium is something that we're going to come back to quite a bit in this class. All right, so we'll go ahead and pause there and again, look at more implications of this in the next video.